Hello and good day everyone. So in this video, we would now be solving for the influence line diagrams for moments of beams. Okay, so as a refresher, when we say ILD or influence line diagram, this is basically a graphical representation on how the location of a load would be affecting the result. Okay, so in this case, we are to deal with moments. So the result we are talking about here is the moment itself. So with that guys, what we will be doing for this video is that we will be graphing what the influence of the location will be, considering that we are to draw the ILD for moments. Okay, so in order for us to do that, what we would be doing is that we will be introducing a unit load. And when we say unit load, unit means one. Okay, so this might be 1 kilonewton, 1 pound, whichever you like, as long as it is one. Then after introducing a unit load, what you would be doing is that you will now be simulating it, or you would now solve for the moment at your chosen position. In our example right now, we are to deal with midspan. So midspan, so what we would be doing is that we would be getting the moment about this point, or its internal moment. Then after doing so, we would now be plotting it in the graph. Then we will now be changing its position. So after here, you might want to draw it here. Then you would now once again resolve for the new result of the moment. Then after getting the new moment, change its position once again, get the new location, then solve for its new moment once again up until you reach the end of the beam. Okay? However, guys, that is practically, or that is actually impractical. So that is very time consuming. So what we will be doing in this video is for us to solve for the moments at the points of interest. Okay? So with that guys, if you would see, or if you are to look at this particular load here, after analyzing the load here in terms of the moment here, so once again we would be solving for the moment here if the load is here. Then after which we would now be moving the load here. Then once again solve for the moment at the midspan. Then at the end. Okay? So take note that this is just for a simply supported beam, and I just want to disclaim that the result here would vary depending upon the setup of the beam. So let's say that the beam is cantilever, or let's say the beam is continuous. It would have different ILDs as compared with what our answer is will be what our answer will be later on, but the process would still be the same. Okay, so again guys, what you would be doing if this is the load, you would be moving it to the point of interest, and in our point of interest, that is the midspan. Why? Because that is what is being asked in the problem. Then here, okay, so we have 3 points of interest here. We have point 1, point 2, and then point 3. Okay, so proceeding guys, if we are now once again to apply a unit load 1 kilonewton at this position. Again, our goal is for us to get the internal moment about the midspan as per asked in our topic here. So in order for us to solve for the moment at the midspan, what we would be doing is for us to cut a section here. Okay, so after cutting a section there, we would be choosing the left side. So let us disregard this. Then again, get the summation of moment about that point. So summation of moment at D. And then whatever the summation of moment at D is, that is basically the moment at D already. So this is what we would be solving for. Okay, so for our sign convention for our video lecture right now, clockwise, positive. Take note that the sign convention might differ depending upon your source. And for American sign conventions, it is actually the other way around. They use counterclockwise positive there. Okay, anyway, so by metric units and by my reference, I would be making use of clockwise positive. Okay, but if you would be getting the moment about this point, we should know, of course, what the result or what the reaction here would be. Okay, so that is the first thing that we would be solving for right now. So let us solve for the value for AV. Okay, so how could we solve for AV? We would be getting the moment about point B. Okay, so summation of moment B is equal to 0, clockwise positive. So from that, we have, of course, the force AV here. So in this case, as you can see, that if you are to apply a moment here, uh, AV would now rotate about point B in a counterclockwise, or in a clockwise direction. So it would now rotate about this point. Thus, it is positive. But take note, guys, that this is, this should be moment. Thus, we must multiply this by our lever arm. And that is now 10. Okay, so another load that is affecting this particular point here in terms of rotation is the 1 kilonewton load. And take note, guys, that that must now be equal to -1 because it is counterclockwise times 10 of lever arm, or times a lever arm of 10, I should say. Then from that, guys, this is equal to 0. So solving for the value of AV, if you want to make use of your computer, or calculators, I should say, you would now be arriving at an answer of AV equal to 1 kilonewton. And if you have watched our previous video lecture, that is quite self-explanatory already, where this is 1 kilonewton because it is directly carrying this load. Okay, so AV is equal to 1 kilonewton. And then, since we are particular with the moment about this point and not really the this force here, what we would once again do is for us to cut a section about this point. So cutting a section about this point, so again, replay. So let us cut a section here. After cutting a section, we would be choosing the left side of the beam. Thus, we would now be erasing this already. Okay? So, again, let us get the moment about D equal to, this is the result or the support reactions. So, this is now for AV, 1 kilonewton. Okay, once again, we are to solve for the moment about D. So, the summation of moment at D is equal to the moment at D already. So, from that, guys, we could now say that MD is equal to AV. So, this is now AV, and that is actually 1 kilonewton times the lever arm. This time, the lever arm would now be equal to 5 meters. So, why is that the case? Because once again, we are considering, or we are getting the moment about this particular point. So, from that, guys, this is times 5. And then, we also have a 1 kilonewton load acting counterclockwise, thus -1 times 5. Okay? And from that, guys, the moment, if you would now put this in your calculators, 1 times 5 minus 1 times 5, that is basically equal to 0. So, the moment at D is equal to 0. So, in order for us to plot this, guys, so suppose that this is already our graph. At this location, if the load is located here, let me just erase what I wrote here first. If the load is located here, what is the value of the moment at D? That is basically 0. Thus, at that location, guys, the value here is equal to 0. So, it is actually as simple as that. Okay? So, next up, if you want to draw, or if you want to pinpoint, or you want to graph what the value for ILD will be, if let's say you will be removing this and you will place the moment, or the force, I should say, at this point. So just solve for the new moment at D, then plot it here. Okay? However, guys, in order for us to save time, we could actually just skip with this location. Rather, let us go straight to our next point of interest, and that is point D, or at the midspan. So if, apologies, the 1 kilonewton load here did not come with the load. So dapat nandito po yan. Sorry po. So anyway, so what would now be the new moment if the unit load will be located at the midspan? So same old, same old. So what we would be doing is for us to solve for first the new reaction of A and get the moment about point D. Okay, so again, let us first get the reaction here in order for us to get the moment. So for the reaction here, we would be getting the moment at point B. So the summation of moment at B, this is equal to 0, y0, because again, as you can see here, this is basically a roller support which does not have any moments. So sign convention, clockwise positive. So next up, so we have here AV, okay? So we have here the value of AV, which we do not know yet, okay? So if you are wondering, sir, hindi ba na-solve na natin yan kanina? So haven't we solved for it a while ago? So that was a while ago. And in this case here, our load was still here. And of course, if we would be moving the load upon a certain location, of course, the result would now vary. Okay? So again, summation of moment is equal to 0 clockwise positive. So that this is now AV times 10. So AV times 10 of the lever arm minus 1 kilonewton, that is now the 1 kilonewton load here, times 5 meters. So this is now equal to 0. Okay? So AV times 10 minus 1 times 5 is equal to 0. Then if you are now to solve for the new value of AV, looking at the calculator below me, so transposing 1 times 5 to the other side. So from that, guys, this is now 5 divided by 10. Or if you want to make use of your shift solve command, feel free to do so. We would just be arriving at the same answer of 0.5. Okay? So from that, guys, AV, as you know it, would now be equal to 0.5 kilonewtons. Okay, so after that, again, we are not really particular with the value of AV. Rather, we are really curious of what the value of the moment at D would be. Okay, but once again, in order for us to do that, we will be cutting a section. So let us cut a section about this point, then disregard the other side, and let us get the moment about this position. So from that, guys, if this is point D, the summation of moment at D, that is equal to MD already. So MD is equal to AV. So this is AV times 5 meters. So this is now the lever arm. So what about for the 1 kilonewton load here? So that is basically minus 1 times 0. 0 having no lever arms. So the lever arm between point D up until the 1 kilonewton load, since it does not have any distance or perpendicular distances, or distance I should say, 0 po yung distance niya. So 0 meters. So solving for that, as you know that AV was or is 0.5. So 0.5 times 5 minus 1 times 0, that is basically equal to 2.5. So looking at the calculator once again. So 0.5 times 5 minus 1 times 0, that is 2.5. Okay? So again, in order for us to, to graph that particular result, if the location of the load is here, meaning the moment at this point is 2.5. So this is 2.5. Okay? So from that, okay, from that, this is now the next point. Okay? So if this is 2.5 kilonewton meter, this is now the next point. So after doing that, we could now proceed to the last point of interest, which is the end line. Again, if you want to draw it accurately, or you want to see the result punto per punto, or point per point, instead of you skipping to the end line, you could check what the result here would be. Okay? So in this graph, guys, in the graph here at the left, so if you would be plotting the result of the moment if the load is here, you would be arriving at the exact same answer, which is, well, this particular value here, whatever that value is. Okay? So its relation would just be a straight line from this point up until this point. Straight line lang po siya. Okay, next up. Again, using this location from that is 1 kilonewton. Using that location, let us get the moment about this point. And in order for us to get about this point, since we are to cut a section here later on, then choose left as the beam that we are considering. Let us first solve for the support reaction at this point. However, guys, as you can see here, since this load is exactly at the top of this support, it has a tendency that this support here would now be carrying all of this load. And if siya po magbubuhat ng lahat ng yan, wala na pong matitira dito. So again, if this support reaction here would now be carrying 100% of this load, the tendency of AV or the tendency of the result for AV is basically now equal to 0. So magiging 0 na po siya. So in order for me to prove it to you, so getting the summation about this point is equal to 0. AV is AV times 10, I should say, is equal to 0, or minus 1 times 0 is equal to 0. So if you would be getting the moment about this point, wala ka pong mapapala, you would be arriving at an answer of AV is equal to 0. Okay? So after doing so, you could now cut the section about this point. So cut the section about this point and disregard this side here. So if this here is the point of interest, or the point where you would be getting the moment. So this is basically MD is equal to AV times 5. So that's it. And substituting all known values, MD is equal to 0 times 5. And calculating any number or multiplying any number by 0, it would just give you an answer of 0. So what this implies is that if the location of the load is at this part of the beam, the result here is equal to 0. So meaning if the load is here, the moment of the midspan is equal to 0. So again, let me just remind you that this graph here is only for the moment at the midspan. If you are to tackle other problems, whereas you would be getting the ILD for the moment at this point, its ILD will not look like this, okay? So again, in my drawing here, this is exclusive for ILD for midspan only. But of course, if let's say you want to get the moment about this point, you would just cut a section here, but you would be making use of the same process. So if you would be cutting a section here, your points of interest for the loads, solve for the result if the load is here, then solve for the result if the load is here, then solve for the result if the load is here. Okay, but then again, in our problem here, we are to deal with a beam, or let's say the ILD for the moment at the midspan, which is here. So basically, this is already our ILD. Okay, so in here, guys, if the location of the load is here, the result of the moment at midspan is equal to 0. Then, if the location of the unit load is here, then the moment at the midspan is equal to 2.5 kilonewton meter. Then, if the result, or if the location of the load is at this point, we have found out that the moment about the midspan is equal to 0. So this is now the influence line diagram at midspan D. Okay, so what this implies is that if the location of the load is somewhere at the middle part, at these parts here, it would now be having a greater effect, I should say, as compared with if the load is somewhere at the sides. Okay, so by looking at this ILD, the interpretation is that the moment at the midspan would be greater if the load is somewhere here in the middle. So as you can see here, guys, if you would be having loads at the supports, basically it does not affect the moment at the midspan. Kasi nga 0 yan. So, even if, for example, you are to put a point load here of 1 million kilonewton. So, even there is the force here is as big as 1 million. Since it will not affect the result, the moment here is still equal to 0. Okay? Okay, so let us now make use of this ILD in order for us to solve for the moment at the midspan if we would be having this load set up. So what we would be doing, just like what we did last video, is for us to project these loads to the ILD. So in order for me to do that, I will just project it there, and as well as for this load here, I would be projecting it downwards. Then as you can see here, I have a uniformly distributed load, so I will be projecting both ends downwards. Okay? So after doing so, what we would be doing here is for us to get what this value is in reference with this graph. So what the value of this one is in reference once again to this projection, and etc. So once again, guys, let me just erase my writing. So let us solve for y1, let us solve for y2, let us resolve for y3, and let us resolve for y4. Well, actually, I have already solved for it. Spoiler. Okay, so again, how did I do that actually? So in order for me to solve for y1, you could actually make use of ratio and proportion. Okay, so if this red line here is 2.5, so if this is that triangle 2.5, its length, or the length of the triangle, so let us consider the left side first. Let us not consider this. So as you can see, we have a triangle here. Apologies for what you are seeing. Pangit ang drawing ko. So let us consider this triangle here. So at the height of 2.5 meters, or at a slope, or at a y component, or a vertical not displacement, or rather a vertical component of 2.5, the horizontal, so from this point to this point, this is basically 5 meters. So where did I get that? So again, as you can see here, this 2.5 meters here is at the midspan, and 10 meters here is, of course, for the whole simple beam, and half of 10 is 5, okay? So this is the ratio of the bigger triangle. So in order for you to get this value, let us now consider this small triangle. Okay? So let us consider this small triangle here. And from that, guys, its slope is equal to y1 divided by whatever this distance is. And according to the problem, that is 2 meters. So y1 divided by 2 meters. And since both of them came from the same triangle, their slopes are basically equal. So the ratio between 2.5 divided by 5, that is equal to the ratio of y1 divided by 2. Okay? So from that, guys, you could now solve for the value of y1. So from that, y1 is now equal to, so from our calculator, so that is 2 times 2.5 divided by 5. So we would now be having an answer of 1. So as you can see here, let me just erase. y1 is equal to 1. So this is what we have solved for earlier. Then as you can see here, guys, this is 2.25. Where did this come from? So again, consider this triangle or big triangle here. Okay? And from that, for the slope of that big triangle, that is 2.5 divided by, again, 2.5 divided by 5. So this is 2.5, and this here is 5 meters. Okay? So with that ratio, that is now equal to, let us name this once again as y2. So y2 divided by, so if this here is y2, this here is y2, this is now its x2, or this is the distance x. So if this, once again, y2, this is x, and x in this case is equal to um 1 meter plus 1 meter plus um 2.5 meters. So that is basically, so 1 plus 1 plus 2.5, that is 4.5. So solving for y2, this is now equal to um 2.5 times 4.5 divided by 5. So that is 2.25. Okay? Then for this value here, you could try solving it your own. So the value for y3 is equal to 1 and the value for y4 is equal to 0.5. So better practice your ratio and proportion skills. So just get the value for y3 and y4 on your own this time as your practice. Okay, so after knowing those values, which we already know now, what we would be doing is that we would be multiplying 50 kilonewtons by the projection here, then add the value of this projection here times, this load here, I should say, times this projection here. And then we would be multiplying 5 kilonewton per meter to this total area here. So why would we do that in the first place? Again, guys, when we have solved for this ILD here, we have assumed a unit load. Okay? So 1 kilonewton. And from that, guys, in this 1 kilonewton load, we are not to make use of that in real life. In real life, in this case, we have made use of 50 kilonewtons. So how many 1 kilonewton loads are there for every 50 kilonewton load? So there are basically 51 kilonewton loads. So from that, guys, if the result here before was basically 1 kilonewton meter, if we are to increase 1 kilonewton into 50, then the result here would also be increased. Okay? So, let me just project this here. So again, this is now our projection. So in me explaining it in another term, so take note, guys, that this ILD here that we created, this is unscaled actually, or this is per 1 kilonewton load only. And as you can see here, this is not 1 kilonewtons, this is not 1 kilonewton, and this is not 1 kilonewton. So since this is unscaled, hindi po siya nakascale, what we would be doing is that we will be drawing, or we would be imagining what the actual results will be. So in order for us to do that, what we will be doing is that once again, we will be multiplying this by this by this, and we will be multiplying this entire, or this 5 kilonewton per meter load to this whole area. So again, if we are to, let's say, scale this, scale po natin itong ILD na to by simply multiplying it, the answer would now be looking like this. So as you can see here, 50 times 1, that is equal to 50. And in here, 5 times 2.25, that is now 2.25 times 5. So 5 times 1, that is 1 times 5. Then 25 times 0.5, that is 12.5. Again, as you could see here, this is basically scaled already. Naka-scale na po yan. Ito na po yung actual. So from that, guys, sorry. Let me just fix that for a moment. Okay. So from this result, guys, so let me just put this at the top. So in order for us to get the moment at D, again, this one right here at the top is already scaled. So again, from the previous slide, it was this scaled ILD here. So this is now to be it. Okay, so in order for us to get the moment at D using our scaled ILD of this loading system here. So once again, once that you have already solved for the ILD, in order for us to get this result using, once again, the scaled ILD, you would just be adding everything. So that is basically empty is equal to 50, that is this value here, plus this total area here, or this area of the trapezoid. So plus 12.5. So this is basically the moment already. So from that, looking at the calculator, so this is now equal to 50 plus 1 half times 2.25 plus 1, so that is 3.25 times 2.5 times 5 plus 12.5. Our answer here is 82.8125 kilonewton meter. So basically, this is already our answer. But if you are wondering, is it required to really scale this first before proceeding to the final answer? So there is actually a shortcut wherein you would not be including this any longer. Rather, if we are to proceed to our ILD a while ago, so just multiply. So again, this is the unscaled. Ito yung original po na ILD na ginawa niyo. So again, this is basically the moment at D is equal to 50 times 1 plus whatever this area is here. Just multiply it by 5 kilonewton per meter. So plus what is the area of this trapezoid, that is 1 half, times. So if this is 2.25 and this is 1, so as you know that for the area of a trapezoid, just get the averages of the two sides, then multiply it by the length. So from that, that is 2.25 plus 1 divided by 2 times 2.5. Again, this is just this area here. So after solving for that area, multiply it by your uniformly distributed load of 5 plus 25 times 0.5. So solving for this value would give you the exact same answer. Okay, so this is 50 times 1 plus 1 half of 3.25, or 50 times 1 plus 1 half, plus 1 half times 2.25 plus 1 times 2.5 times 5 plus 25 times 0.5. So the answer is still the same, and that is 82.8125 kilonewton meter. So you could also compare with the result if you would not make use of ILD. So the answer should be exactly the same. So there.